So welcome to this special Theoretical Astrophysics seminar. We have a guest who is actually an SNF mobility fellow, Leila Haegel, and she's gonna talk about some interesting aspects of the analysis of gravitational wave signals and the connection with machine learning. Before she starts, I'd like to briefly introduce her. So Leila completed her PhD in 2017 at the physics department in Geneva. And at the time she was working on neutrino physics. And then she moved on as a postdoctoral fellow at the Balearic Islands, the physics department over there, University of Balearic Islands, working in the gravity group. So that's where she started to move to the field of gravitational waves. And she worked on a phenomenological model for waveforms. And then she started in 2019 her mobility fellowship from SNF, hosted at the University of Paris Diderot, where she's diving deeper in the important problem of parameter estimation of waveforms, which is relevant for the current data of LIGO and Virgo, but of course will be very relevant also for LISA, Einstein telescope, and all the future gravitational wave experiments. So I think I leave her now to talk about this today.
Thank you very much for the invitation. I think most of what is on this slide has been said. I'm a member of the LIGO-Virgo CAGRA collaboration, so we detect gravitational waves and we do physics with those detection, also to detect them. In the last years, there have been a start of applying machine learning techniques to enhance some part of our analysis. This is something that is more and more increasing because there have been promising applications, and I'm going to review some of them. So this talk is kind of separated in two parts. In the first part, I am going to describe a little bit gravitational wave physics, the connection with general relativity, how we detect the gravitational waves, the detection and analysis techniques, an example of the importance of the physics results that we have when we analyze the signals. And in the second part, I am going to give an example of few applications of machine learning algorithm. My expertise is more for the modeling of the gravitational wave and the estimation of black hole parameters. However, I have been also involved in other projects to detect the gravitational wave signals. I've also been very interested in application for the estimation of the source parameters. I'm going to review the different tests that have been done on those lines as well. So let's start a little bit with the physics of gravitational waves. Gravitational waves come from a theory of general relativity. If we're going, for example, in the weak field limit, where we can linearize the Einstein equation, then we see that there is a wave equation actually coming out of it. And as the theory was more and more delved into the stronger field regime, it has been shown that actually this wave equation were corresponding to wave that were stretching space-time, and that's a gravitational wave. When we have a gravitational wave propagating, it's going to modify the space-time interval as given in the ds square equation that is here. And on this equation, we can see that in general relativity, a gravitational wave is going to propagate at the speed of light. And it's a transverse wave. If it's going along the z direction, the stretch is actually going to occur, the deformation along the x and the y direction. There are tensor perturbation, which means that the space-time stretch is actually of quadrupolar mode. Because of energy conservation, there is no monopole radiation, and because of momentum conservation, there is no dipole radiation. In terms of polarization, a gravitational wave is quite similar to an electromagnetic wave in the sense that we have two polarization, H plus and H cross. However, the difference with an electromagnetic wave is going to be the angle between these two polarizations is going to be 45 degrees and not 90 degrees. We know that the gravitational wave is not an artifact of theory, but a physical effect, because it is actually going to create a fractional change in distance between 2 points. And that's what we call the strain, and that's what we detect with our interferometer. And we can see on the bottom the kind of an easy way to see the deformation that we'll have when a gravitational wave passes through is to look at a ring of test masses. As a gravitational wave passes through, the two polarization, the H plus on the top is going to create a deformation along the horizontal and vertical axis, while the cross polarization on the bottom is going to create a deformation along the diagonal. So there is a physical effect and we can actually measure it. The source of gravitational wave, as I said, it's any accelerated mass. However, gravity being a very weak force, we will not detect any accelerated mass. We are detecting cosmic events. The strain that I just described is for those cosmic events usually following a wave equation. So we can kind of model it as having an amplitude varying with time and a sine wave of a frequency varying with time also as the dynamic of the system is evolving. And the amplitude is going to decrease from the source as the gravitational wave propagates in space-time. However, although the effect is very small, we are not detecting the gravitational wave from the events that have the largest strain amplitude. The supermassive binary or the cosmic microwave background gravitational waves are actually having a very low frequency. And at this frequency, we cannot not even detect a strain of 10 to the minus 10. In the frequency band of the LIGO-Virgo CAGRA, the ground-based interferometers that are operational right now, we are detecting actually the merger of neutron star or stellar mass binary black hole who have a smaller strain but a higher frequency that correspond to the event that we can see with our detectors. A little more about this interferometry technique. How do you detect a variation of a space-time interval? If you take a ruler, the molecules of your ruler are actually gonna get closer together or are gonna be further from each other. So you won't see it with your ruler, except if your ruler is made of light, because with light, you always travel at the same speed. This is why all the gravitational wave interferometers are based on having at least 2 lasers. In the case, it can be more, but in the case of the ground-based one, we have 2 arms with one laser that is actually splitting the light of the laser into the 2 arms. Then in the end of the arms are mirrors that are sending back the light that is recombined and reaching the detector. Therefore, the 2 light waves that have been traveling in the 2 separate arms are recombined, and the interference pattern when they are recombined is the signal when there is no gravitational waves. But if a gravitational wave passes, the length of the arm is gonna be longer, and it's gonna be different according to the polarization of the arm. Therefore, there is going to be a difference in the path of the light signal, and the recombination is going to be different when it reaches the detector. This is this new interference pattern that we are going to detect, and that is going to tell us that a gravitational wave has passed through. This is a very long and complicated technique to go from this interference pattern to actually signal of a gravitational wave. So there are a lot of steps in the analysis, from controlling what is happening in the interferometer to actually linking the interference pattern to a gravitational wave signal, and then to analyze the property of this signal. We have currently 5 observatories working in the world. There are the 2 interferometers of LIGO that are located at 2 opposite sides of the United States. The further the interferometer, the better is the detection of the localization of the signal on the sky. The third one is Virgo, that is a European project located near Pisa in Italy. Virgo has 3-kilometer long arm lengths compared to LIGO that has 4 kilometers. GEO 600 is one of the smaller versions that has 600 meters. That was a step into creating LIGO and Virgo, and is still part of the LIGO-Virgo collaboration. It doesn't have enough sensitivity to see the astrophysical signals that the other detector detect. However, it is used a lot in order to improve the detector characteristic, to do some R&D. And recently we have Kagura, the Japanese interferometer that has joined us. That is also a 3-kilometer arm length interferometer. The more interferometer we have, the better is the localization of the signal in the sky. Starting from 3, we can do some triangulation. If there are 4, we're getting better localization. And in the last run, we were having 3 detectors during half of the time, and 1 detector only 15% of the time. Know that Kagura is going to join us for the 4th run. As the sensitivity is going to increase, we will have more time where we have 4 or 3 detectors, and we will have more time where we'll be able to actually localize the signal with better accuracy. In India, there is the project of having a 5th detector that is like LIGO. It's a LIGO detector that's actually available. And there is a plan, currently they are planning where to build it before putting it under construction. And then we'll go to a 5 detector network. In terms of sensitivity, on the bottom left, there is a plot that is showing the initial and advanced LIGO design specification. Basically, everything is going to be above a black line is going to be a signal that can be detected by our interferometer. The initial specification has been already reached without seeing any signal. After the initial specification, the initial design being reached, there have been a second phase called Advanced LIGO, and we are currently in the Advanced LIGO and Advanced Virgo phases, where the detector improved. We are currently still improving the detector to reach the Advanced LIGO specification. So our current sensitivity on the bottom right, you can see the sensitivity that we had at the last run is basically between those 2 lines. What is creating sensitivity is our source of noise. What we can see is that low frequency, the reason of having a high noise that is very quickly reaching very high amplitude is due to seismic noise, that is any noise from the ground, or noise of the mirror, such as the coating of the mirror, the thermal noise of the suspension that are having a strong effect on our detection ability. This is why the next interferometers are planned to be in space, like LISA, is to get rid of the seismic noise, being in a colder environment that's going to enable us to detect signal at lower frequency, and that's where we will be able to see the supermassive binary signal that I was showing in the plot before. At higher frequency, it is a little more complicated because it's actually what we call quantum noise in the Heisenberg uncertainty of the number of photons reaching the mirror and the detector. This is something that comes from our quantum theory and is very hard to be more clever than quantum physics. There have been some improvement in the between the last 2 runs using what is called the squeezing method with entanglement of photons in order to improve our sensitivity at higher frequency. However, this is a part that requires a lot of creativity to be able to improve our detection in this frequency range. And this is still a very active R&D program. As I said, so for this range of detection between about 20 Hertz to 200, 300 Hertz, we are going to detect the coalescence of compact binary. There can be binary neutron stars if they are quite close, because neutron stars are small stars in terms of mass. Therefore, if they are very far away, the signal is going to have a too low amplitude to reach us. If they are quite close, we have detected already the coalescence of a neutron star binary. Or it can be stellar mass black holes. And when I say stellar mass, I'm saying from the neutron star mass, so 1.4 stellar mass, to 200, 300 solar masses. We can also detect other type of signals. For example, we can detect what we call continuous waves, waves that are continuous, that have a single frequency from pulsars. And then they're going to be appearing in the bottom right plot as a line. You will basically have a signal as a single frequency, very small amplitude, but because it's continuous, you will have this line of certain frequency that is going to be higher and cumulative. Those events, because they're small, are hard to detect, and also because we have so many lines in our signals that are due to power tension, instrumental artifacts, environmental artifacts. We have not detected continuous waves right now, but as we are having a better sensitivity, as we are increasing the time of observation and adding runs, this is something that we expect to see in a not so far future. How do we actually detect and analyze the signals? During the O3 run or detection range that we characterize our detection range from a binary neutron star range, because binary neutron star always have the same mass. It's not like the black hole that can go to like 2 or 3 orders of magnitude in masses. So what we see is that we almost doubled, well, more like a third better the neutron star range compared to the second run. And with the Livingstone detector, we reach 135 megaparsec for a binary neutron star. For black holes, we have detected black holes that are more than 5 gigaparsec away because they are more massive. And to detect events from the coalescence of compact binary, we have different pipeline search. For our modeled search, that means that we are actually comparing what we receive to a model of signal, and to our unmodeled. They're going to see there is an excess of power in the detector, and they're going to say, here there was an excess of power, it doesn't seem to be noise, there might have been something. And this is very important to have the two, because with model search, they are kind of more accurate for signals that we know. It's easier to, if you have an idea of what you look for, it's easier to find it when it's a small amplitude. But unmodeled search, they enable us to go beyond our current theories. If we have an event that from an exotic compact object that is absolutely not described by GR, or that we are not having in our model search at least, then hopefully, if it's strong enough, the unmodeled search pipeline is gonna tell us about it. We have a database, it's called GravitySpy, that is available for the public, where automatically when we detect event is going to give information about this event. So now there is an example, there was an event, and from our automatic analysis, it seems to be consistent with a binary neutron star. And here is the localization in the sky where it is. The sky localization is important in the case of a neutron star, because then we can send alert to satellite and telescope that can search for electromagnetic counterpart. And if we see electromagnetic and gravitational wave signals, then we can do very interesting physics, cosmology, tests of gravitation by using the two information at the same time. In terms of model search, we need to know what we are looking for. And this is why we need to have a model of the signal. We are using, so there are different ways of having a model. Solving Einstein equation actually require numerical relativity simulations, and those simulations are available, but they are very computationally intensive. We need supercomputer to be able to solve Einstein equation. Therefore, we usually rely on Bayesian analysis on approximate model. And what we can see about the signal that we have is that during the spiral phase, where we have a large distance between the object, we have a waveform that has a low frequency, low amplitude. And as they get closer, the frequency and the amplitude is gonna be increasing. And this is a part usually where both the frequency and the amplitude are going to enter our sensitivity band. And when we have a final black hole, it's going to relax during a period called ring down until getting a novoid shape, as is usually a Kerr black hole, because even if the initial black hole are not spinning, most of the orbital momentum is transferred into a spin for the remnant black hole. So this is a type of wave that we see in our detector corresponding to this type of dynamic for a binary system. What is very complicated is that actually those waves usually have the order of magnitude of the signal. Therefore, we cannot just analyze a shape that we would see very well in our detector. What we actually see is more something that looks like the blue shape. And we are trying to see, so we see an artifact between 50 and 100 in time unit, and we would like to know, is it actually a gravitational wave? To know that, what we do is that we rely on the match filtering technique, where we are going to compute the correlation between a template signal and the data in the function of time. So as we start with our red template being at the beginning, we don't see a high correlation between the data and the template. However, as we keep going around the signal, we are going to see that there was a phase where there was a high correlation. And that's from this type of metric that we build our SNR, both for the detection, but also for the estimation of the source parameter. Match filtering has been shown to be the most powerful technique for very small to detect and to analyze signals that have about the same order of magnitude as a noise. And then from this SNR computation, we are going to sample the source parameter, and we usually rely on a Markov chain sampling of the Poisson probability parameter of the source, where we have 15 parameters actually to describe a binary system. This is the minimum considering that it is black holes. If you actually have neutron stars, you need to add tidal effects. If you have black holes, you already have the masses of the black hole, the spin magnitudes, the angle for each spin. There are 2 angles for each spin to characterize the precession. You will have the reference time of the times they are actually merging, the orbital phase that they have for the binary system. And there you also have the distance of the binary on the line of sight, the right ascension, the declination to be able to localize it in the sky, and the inclination of and polarization angle of the binary system in the sky. So this is already quite, even although black holes are extremely simple systems that are only characterized by a mass and a spin, when you take into account that they are in a binary configuration, this is actually creating already a system with a large number of parameters to be able to describe it. A little bit like some example of interesting physics that we can do. We can analyze the astrophysical distribution, and we just have released our detection from the first part of the 3rd observational run of LIGO and Virgo. And what we can see that actually the distribution of binary black hole that we detect is quite different from the power law distribution of binary stars. So this is opening new questions about do they actually form more in globular cluster? What are the dynamics of the the environment of the black holes in the sky? So this is really something that is, this type of analysis are really statistical analysis. And with the last catalog, we are now reaching to 50 detections. This is why we're starting to see deviation from what we already know. And as we are having more detection, we're going to have much more insight about having this new channel of black hole detection that is going to enable us to understand better the dynamical objects that are in the cosmos. As I said, for a neutron star binary, we can have an electromagnetic counterpart. This happened in 2017, and this was very interesting because if you have an electromagnetic signal from which you can infer the luminosity distance and a gravitational wave signal that you can compare to, then you actually know both the redshift and the distance of your object. Sorry, from the light you actually get the redshift, and from the gravitational wave you get the distance. This is what is called a standard candle event, because if you know the redshift and the light with one object, then you can measure the expansion of the universe and the Haegel constant. So with one event, we actually cannot compare with Planck and supernova measurement right now. I mean, we are consistent with both events, while those events are slightly in tension between each other. However, as more events are going to be added, we need about 50 events to have a better, to be able to disentangle between the two results. We will have another totally independent measurement of the Hubble constant, which is of interest for cosmology measurement. We can do a lot of fundamental physics. By having the first direct detection of black holes, we have opened really a door to fundamental physics and also probing the nature of space-time with the different canals and astroparticles or electromagnetic wave. So when we study the propagation of the gravitational wave, we can actually constrain the mass of the graviton. And from the dispersion of the gravitational wave, we can constrain alternative theories of gravitation, such as scalar tensor theories that are very popular to describe the dark energy. Alternatively, when we study the ring down that I described to be the end of the gravitational wave signal, we can try to really probe the nature of black hole. For example, we can test the no-hair theorem to know if it's really a black hole or an exotic compact object. And if we would have an echo, so we can probe if the black hole is actually having a structure that has been proposed by some people to actually solve the black hole information paradox, where you would have a type of envelope with a firewall. This would create some echoes in the gravitational wave signal that we would be able to, that we might be able to see. For now, we have been looking for exotic compact object or echoes, and we have not detected them. So for now, everything is consistent with GR, but we are just at the beginning with low SNR events. So we are really starting this analysis. And as we are going to have more instruments with better sensitivity, even future instruments, this is where we're going to reach the level of precision where we think that we will have a real door in probing fundamental physics. So this was my overview about gravitational wave astrophysics. And now I am going to go a little more in which aspects can be enhanced with machine learning. First, why machine learning are useful for gravitational wave analysis. We have very small signal, as I said, and this is where we need a really clever algorithm to be able to analyze our signals. But we also have complex systems. As we saw, binary systems have a lot of parameters to describe them, and the Einstein equations are nonlinear. It's a complex physics in the strong field regime. And this is where algorithms that are known to appropriately find correlation in high dimension systems are useful. That's very linked to the high dimensionality of the system. There is also the fact that solving Einstein equation, due to this complexity, it requires numerical relativity simulations that are so computationally intensive that they do not span the amount of, they do not span all the configuration that we have in nature. So we cannot use our most accurate simulation to actually do the parameter inference that we want to do, to actually do our analysis. Therefore, we need to rely on approximate simulation. And some of the machine learning algorithms are helping us to design better approximate simulation in this high dimensional system. I have selected few examples that I think are giving a little bit of representativity of application, and also that I've been involved or interested in, so that I could present them to you. But there are actually a lot of work for a lot of things that I'm not talking about, detecting gravitational wave from pulsars, disentangling the model of supernova explosion. We have written a review article that has been published in Machine Learning Science and Technology and is available on arXiv, where you would have much more examples about what we can do and what we are doing. Let's start with characterizing the detector noise. Our detectors are very noisy. They are detecting a huge amount of things that are due to the instrument, like we can have some light scattering inside the lasers and reaching the detector, or you can have train passing by, an earthquake. We are detecting a lot of things that are not gravitational waves. And when they are transient signal, usually non-stationary and non-linear, then we call them glitches. We need to understand where they come from, because we need to understand the noise in our detector so we can improve it. And we also need to know, I mean, we have a lot of events where we have a glitch at the same time as the event. This is an event from the third observational run I'm showing on the right, where we can see that in the spectrogram. So this is what it calls spectrogram. This is the frequency, beams of frequency in terms of time. And when it's yellow, it means that you are actually having something seen by the detector. And we can see that we have these two yellow blobs that we have subtracted from a signal so we can analyze it, because it was actually created by glitches. The thing with glitches is that they have different morphologies due to their origin. And when we go in this spectrogram way of seeing the signal, then this time frequency map is actually very similar to a picture. And what we've seen with the recent application of machine learning is that convolutional neural networks are very good at actually classifying different pictures according to their morphology. So there have been quite some application to actually classify the different type of glitches of transient noise using CNN. So in this example that I'm showing here, that is analyzed by Razzano and Cuoco, they use a supervised learning on simulated glitches. And that was one of the first analyses that was done with simulated noise. And they already find a 99% classification efficiency when they have the structure shown on the right of different CNN being put around each other. So we have we had this hint that actually we could classify the different type of noise very efficiently. However, we need now to move to actually classifying not simulated noise, but real noise. And to do that, because this is a supervised learning approach, that means that the classes are defined beforehand, which means that we need database where we have a lot of events that have been classified. This is a very complicated project that requires a human part, and that's why there is a citizen science project called GravitySpy. There's actually an app, or can be done, I think, also in the browser, that anybody can download. And when you download it, you are provided with example of glitches and a little training telling you this type of glitch is what is called a blip or a helix, according to the morphology. And the users are being presented with several types of glitch, and they take the time themselves to actually say which type of glitch it is. This is creating a data set on which we can actually apply machine learning techniques to, this is creating the training set for a CNN where we can actually see the efficiency of CNN on our own data. And that what has been done is this paper by Zevin and many other LIGO collaborators, where they are using the citizen tagged event to actually create an automatic classification of the noise. And what they saw is that for most of the events, they were very close. Most of the categories, they have about 100% correct tagging efficiency. The other one are about between 95 and 99%, I would say. However, the categories of paired dove that is shown here, and the wandering line that is not shown here, but it's basically a line that can be anywhere, somewhere, are very hard to tag. And there is some crossover with other categories, such as, paired dove and the helix can sometimes be a little similar. So this is a very interesting application of creating a citizen science project that have been very successful. There is a forum around it, has been used to teach about gravitational waves in schools. And that is also creating a data set that is actually very useful for us to understand the noise of our detector and to know how to improve it. Let's move now. Know that we have, when we have glitches, we also have the question, are there actually glitch or are there astrophysical signals? And to be able to distinguish between the two, we can use what is called auxiliary channel. So beforehand, I show a very simplified description of the interferometers. But the interferometers are extremely much more complicated than this. They have actually a huge amount of detectors, subdetectors on the line. Here is an overview of few of them, but they are actually, I think, on the order of 1,000, what we call of those auxiliary channels that are recording constantly the status of the detector. And the question was, can the data from this auxiliary channel help us to actually make the difference between a glitch and an astrophysical signal? And the answer is yes. Using this data, there have been several algorithms that have been implemented and that have been compared in order to see if we can distinguish between a transient signal, if it's due to noise or not. There was an artificial neural network, another one based on support vector machine. There was a random forest application and a kind of dedicated algorithm called ordered veto list, where it's creating correlation between the signal in the auxiliary channels and doing a hierarchical ordering of the correlation in order to see if it's a glitch or a gravitational wave. They have been comparison of all those algorithms during the initial LIGO phase that have shown that they were more or less kind of behaving the same. I mean, more or less, the artificial neural network is slightly different. What is quite interesting is that we have restarted to compare those different solutions with the advanced LIGO phase. And we're now seeing some difference where the ordered veto list is actually behaving much better than the other one. We're in the process of trying to understand if we need to refine the other algorithm. Maybe when they were actually created, we didn't have such a good sensitivity. We didn't have gravitational wave events. So maybe they need to be adapted to the new sensitivity, while the ordered veto list, apparently from its hierarchical ordering of the correlation, can capture the difference better. At this point, the ordered veto list algorithm is implemented and is being used by LIGO to subtract glitches, to not analyze the transient noise. So this is a concrete application of an algorithm that is currently used by the collaboration to veto some signals that are not of interest. Let's move to modeling gravitational waves. Because we rely on the match filtering algorithm, we need to compare templates to our data stream. That means that we need to have templates of gravitational waves. Those are modeled analysis, supervised analysis, if you want. However, as I say, the numerical relativity simulation, we now have catalogs that are on the order of 3,000. While if you want to do Markov chain sampling, you are in the order of 10 to the 5, 10 to the 6 steps minimum to have a proper posterior probability, which means you cannot rely on those numerical relativity simulation. You need to have approximations that are being able to span the whole part. If you are in what is called the inspired phase, where the two objects are separated, you have a weak field, then you can model this part quite well with a post-Newtonian formalism, or what is called the effective one-body approach that gives a very good signal in this regime. But as you go closer to the merger of strong field, then this is a part requires numerical relativity, and it can basically be approximated by some ansatz if you want to reproduce it. The ring down part is something that can be modeled analytically with a sum of damping waves. So an important ingredient when we are modeling approximate solution of the signals is to infer the properties of final black hole based on the initial black holes. This is important basically as we design a signal to see that the signals that we are designing, the approximation that we are designing, are correctly predicting the remnant black hole that is evolving from the system. And the issue is, that is a general issue as we were talking about modeling the effect of the dynamics in the gravitational wave signals, is that if you go to a quite simple system where you have short-shielded black holes that are not spinning, then you have a lower dimensionality because you ignore the spin. You put that the spin is 0, and then you just have the two masses that are what is called the intrinsic parameter that are going to govern shape of the signal. And then the orientation of the binary can be parameterized externally. That's called the external parameter. So basically, if you have just the mass and maybe, or if you have a line spin, you don't have a precession effect. This is something that has quite a low dimensionality, and that can be, and then you can infer the properties between your initial black hole and final black hole, or usually even your waveform quite well. However, once you start to have the black hole spinning and inducing precession, and we have seen example of black hole spinning in our third run. So this is a case that exists in nature. And this is a case that is actually important to understand the formation channel of black holes. Then the whole system starts to have more dimension, and it's actually harder to rely on just approximation with ansatz because we just don't see in that many dimensions. So there have been some application using neural networks and Gaussian process that were the first applications that were really taking fully into account the precession and that were able to map the properties between the initial black hole and final black hole with very good accuracy. And this is an example. This is the error that is coming from one of my articles where we have applied the neural network. What we can see is that what is in yellow and in purple were fits that were approximating the precession, and they had a bias in estimating the final mass. They had the same bias in estimating the final spin. When we are properly putting all the vector of the spin as an input of the training data instead of approximating to one or two angles that are projected, then we see that we can correct this bias, and the neural network is much more efficient in predicting the final mass of the black hole, and we have the same result for the spin. But beyond just predicting the final properties of the black hole, we want to be able to provide a gravitational wave signal. And a gravitational wave signal is a much more complicated thing than just a list of a number, because it's basically a list of number evolving with time. And usually the approximate signal were given with either this effective one body approach or some augmented post-Newtonian for the first part. And then there were basically some functions that were designed to look like what is given by numerical relativity, but they didn't have, they were basically some very, very elaborated trial and error. So let's try this function, does it work well? Do I need to add more parameter? Let's try several function, let's use some information criteria to not put too many parameters, but still have a correct fitting. What has been shown is that an alternative to this is to use Gaussian processes. Gaussian processes, you basically have this map of Gaussians that are across your parameter space. And when you train a Gaussian process, what you do is that you adjust the mean and the standard deviation of all those Gaussian and the correlation between them. You have a correlation matrix. So they can actually mimicate the signals that you have as input. But not only they're going to mimic a signal that you have, actually, because it's a space of Gaussian, it's going to create an interpolation between the point. And in one of the first application where it was Q is the mass ratio between two black holes and you have the two spins. So here is an example of input training data to show the parameter space covered. a Gaussian process has been trained to actually look like the numerical relativity waveform that we had for all those points, but also is providing an interpolation between all those points that is shown on the left. So on the left in black, you have the numerical relativity signal that is our most accurate gravitational wave signal that is used to train the data. And in orange, you can see how the Gaussian process is reproducing it accurately, more accurately than other methods based on approximate approach. And what is very interesting with this process is that when you have a Gaussian process, the shape of it is also going to incorporate the uncertainty, the interpolation uncertainty between 2 points. So afterwards, when we are using a waveform to do parameter inference, then we can also propagate the uncertainty on the waveform that is currently not done in our analysis. So there is an uncertainty that for now we know is very small compared to the SNR that we have and the other source of uncertainty. This is why we neglect it. But we know that this error is going to be important as our sensitivity is going to increase, and we need to take into account in our error budget. And with the Gaussian process, this is something that can be very naturally done by sampling the Gaussian process that has been trained, actually by extracting interpolated waveform several times. Then it's going to create an envelope that is going to be the uncertainty due to the interpolation process. As we're talking about estimating the source parameter, let's have a quick look about tests that have been done in this direction. So I have said that we usually use Markov chain to sample the posterior probability on a source parameter, and the problem is that this is a very slow process. We usually use Markov chain Monte Carlo with a Metropolis Hastings algorithm or parallel tampering, address tampering, or nested sampling, but it can take of the order of days or weeks to have, according to the SNR that we have, according to the length of signal, to have a posterior. So there have been some tests to actually apply machine learning to be able to have, to speed up this process, to train, knowing the interferometer sensitivity, knowing the type of signals that can be detected. There have been some tests training a conditional variational autoencoder that is a machine learning algorithm that has like what is shown here as E are actually encoders that are made with neural networks that are, some are convoluted, others are just fully connected, and has been designed in order to be able to reproduce the posterior sampling. This is something that if you go to this article by Gavar and al., that has been shown to be able to reproduce the posterior probability in many cases. However, first, it's hard to tune. That took a long time to develop this. If you study a little bit the shape of the algorithm, you see that not only you're training with your data, but in the training phase, you kind of need to inject your source parameter somewhere in order to make the whole algorithm understand, kind of converge to the true parameter. There is also the issue of this is working in 99% of the time, but you don't know the time it doesn't converge. You don't really have a metric of the day it will not work. And this is, although this one strain enabled to have a result in the order of the minute, there are some concern about the convergence of the algorithm and how often it's going to give the right results. So we are not yet using it on a production basis. And this is the same case also for normalizing flow, where there have been also some there have been some attempt to basically use this process of creating a set of transformation where we would have a multivariate Gaussian at the beginning, and then there's a set of transformation that is going to transform it into a more complex target distribution that is here opposite our probability density of the source parameter. And this is also working very well. This is in green, it's I think the Monte Carlo, and in blue, it's a normalized flow. This has a very good efficiency, but there is a lot of work to do to understand if we can actually rely on this or not. And I think it's unusual. This is one of the questions with machine learning now is, and this type of algorithm is, how often does it converge? Can we have some metric to know that sometimes it doesn't converge? Or if we need to check our signal with a Markov chain after, then it's probably not that useful to actually run it. So this was all for me. As I said, there are many more examples. So if you're interested, do not hesitate looking at our review articles. Do not hesitate also looking at the archive, because there have already been new applications since we wrote the review article. We have what is called GTUNet here. That is a cost action that is linking gravitational wave and machine learning scientists together. So you can look, we have a Twitter, we have a website, you can look at it to have some news on the application that we're doing. And thank you very much for listening. Any question is welcome.
Thank you. Thanks a lot for a very nice talk. So we can start with questions from the audience. Let's see if I can see some raised hands. Okay, I don't see now anyone. Okay, so okay, now there's one, Prasanjit. Please go ahead.
Hello. For the actual implementation, do you have specialized hardware, or is it TensorFlow or something else again?
It really depends on each algorithm. I think most of us are using TensorFlow, but I think some people are using PyTorch. And for the implementation we're using, I mean, in terms of computing infrastructure, we have what is called the LIGO data grid, where we have CPUs and GPUs. So we have some machine with GPUs that are kind of dedicated to this and maintained for this.
Thank you.
Okay, let's see. Okay, while the next N appears, I will ask you a question. I was very interested in this part where you describe the interpolation between, different numerical relativity simulations. The examples that are shown here, are these for, I can imagine that they are for circular or quasi-circular binaries, right? Because as far as I know, that's one of the bottlenecks now for numerical relativity simulations, and also for other methods, is to be able to model the eccentric binaries. Is there any, so at the very beginning, you also mentioned this important point of unmodeled sources, right? So of course, the eccentric binaries are not strictly completely unmodeled sources, but because they are a bottleneck in the current modeling, I wonder whether the machine learning could work also to interpolate in a regional parameter space where essentially you have no bona fide data to train on, because we don't have yet simulations of very eccentric binaries, but we might, use a combination of methods to, somehow completely fake the waveform of an eccentric binary and then interpolate.
Yeah, it's a good question, because I don't think, I mean, we could try this, right? We could inject an eccentric signal with different degree of eccentricity and see how much we recover it with this type of, this modeling approach, we call it surrogate modeling, this interpolation is implemented in our software. And this is an analysis we can do to see if it recovers some eccentric binary. I mean, we could basically test several models. Yeah. I don't think it has been done. I haven't heard of it. Yeah. Philip, who is listening to us, knows more about eccentrics than me, so he might know.
Yeah, because this is really, even in terms of, even for Lisa, I mean, we spend lots of time talking about we will be ready or not with, enough, templates from numerical relativity simulations by the time we will need them? Probably not. I mean, they might cover just pieces of the parameter space, but here you might fill the gap in some form.
I think that, I mean, so it's true that we only have a handful of eccentric numerical relativity simulation. However, what is interesting is that the people who are actually designing this model, so I start to be interested in this model and to be active in this type of search. But the people who initially started this application, they are in the same group of people that are doing numerical relativity simulation. So there is this discussion of what type of numerical relativity simulation do we need, how do they actually cover the parameter space. So there is a possibility that even if we have a handful of eccentric waveform, we might be able to add this as a parameter and to have a first interpolation. And what is interesting is that with this, if we train with this Gaussian process, then we will anyway have an idea of the error of the interpolation. So we can see from the output, are we actually ready, or between 2 points, are we actually 3 times the eccentric effects? That would be very interesting to have an application for that.
Yeah.
But I think, I think this requires also what Leila was somehow implicitly saying, that you need to have a lot of also somehow computed models, eccentricity models, in order to be able to compare. So one way is also probably to go with this EOB. I know that there are people who are studying EOB with eccentricity. And if this would also help to have then, say, a lot of examples on which then to check with the machine learning and somehow to get to the point.
Yes, EOB are usually used for the training part of the Inspirer, at least.
Yeah. More questions from the audience? Let's see. Let's going with this. Okay. Yeah. So and here's, sorry, because I don't see ends now, so I keep going in the meantime. Okay, so instead in the part that you discussed at the beginning for the application on the noise, the citizen science project, basically, how what's that exactly done? So here. There was a kind of fake data set created with glitches, or I just didn't follow exactly how this data set was created.
No, this is a real data set from our instruments, where basically there is a first determination that this is a glitch, this is not a gravitational wave signal.
Okay.
That has been done, and this is fed to the human to say, okay, we basically say to people, if you have the app, you say, this is a glitch. It has this shape, so it's going to be one of the squares. What type of glitch it is? Like, what do you, for you, what does it look like? Does it look like paired dove or a blip or a koi fish?
The characterization, okay.
So it's really to characterize based on the morphology. And the idea is that basically different morphology are going to be due to different source, like scattered light has specific morphology, power line too. Yeah. But others can actually be a combination of sources.
Right, but then, but how is the noise? Because of course there's always the issue of the noise in the extraction of the signal. So the noise is also in a kind of, how is it? Is this just a standard instrumental noise that was already built in, or would one have to, for example, if you do this for a different instrument, which is not yet here, like LISA, would you have to do simulations in advance to see, which shapes you're able to recognize depending on the noise level?
Yes, so I think that was kind of what was done. So this first analysis was with simulated noise, and there they could see that they could really classify very well. And then we moved to real noise because we want to see the effect on real noise. And that's where we needed a data set that was tagged. And that's where the citizen science project started. So I guess if we have LISA, we could do in the first time for simulated noise. And eventually have this same, I mean, citizen science, or just have a team of people actually analyzing the real noise when the instrument is done.
Yeah. Okay. Okay.
I mean, they're always surprised when an instrument is done, usually, I guess. But what is kind of optimistic is that for most of the categories, once the tagging was done, then the classification happened and occurred, at 99%, 100%. So we see that the simulation is working well for most of the categories. Then there are a few, as I said, that are working less good, and that also enables you to put most of your energy on the categories you can classify very well. But also there are other, I mean, this type of paired of events, for example, I tried a little bit this GravitySpy app, and it's really nice, but usually there are some glitches that are much more frequent, like the bleep, the koi fish. I think, I don't remember all of them, but some are extremely frequent, and you just have a bigger training set for them. Maybe the paired doves are just occurring much less. And if we have a first idea for classification, then we can provide them more to users, so have a bigger data set and train a little more.
Okay, any more questions from the audience? Just checking if there is someone in the chat, but not. Well, I guess maybe people will think over possible questions and ask them by email.
Yes, don't hesitate reaching by email, and I'd be happy to answer or point to any useful reference.
You're going to be here and for another week. Do I understand correctly? In Zurich, I mean.
Probably a little more than another week. I mean, I'm not it depends a lot on the pandemic, so probably a little more. But exactly how long is kind of hard to predict. Yeah.
Okay. Okay. So I guess thank you a lot again for the very nice, interesting talk. And so I hope people will come back with more questions. Okay. Thank you very much, Leila.
Thanks to everybody. Have a good week.
Thanks a lot.